the fourth of 5 of the buffer overflow series. This one is called corrupt ret, which will make sense by the time the challenge is over. So from the prompt, it says, can you overwrite the control flow? The goal is to overwrite the previously stopped instruction pointer to jump to do valid stuff. How does the ret instruction pointer stack work on x86? That's the fun part. That's where the magic of this is at. And it says, hint, the offset is hex 30 bytes, which is going to be 48 in decimal. So we're going to go back to computer architecture class, and we're going to talk about how this works. So when I call a function, the way this works is it will push the return address to the stack. Say we're right here. Then it saves the base pointer, which is the local stack frame information. You have some local variables that could be stored, and then you have ESI and EDI and various other registers depending on the architecture. But the thing we're after is this return address. Just like before with how we edited the function pointer, if we can corrupt this, then we can corrupt the control flow once again. Except of doing it on a forward side, we're doing it on a backward side. This happens when we leave a function. When we leave a function, it does everything in reverse. It restores ESI and EDI, and it restores EBP, and then it's going to call ret. And under the hood, ret is just going to move the item that's currently on the stack into the instruction pointer register. So this is the fun part here. Now, if we go to the terminal here, and I have left over from the previous challenge, we can log in. What is this challenge called? Wrong challenge. This is called corrupt ret. So we can just log in. Same username and password, or the username and password exactly the same as always. So if you go to corrupt ret, this one actually looks a tad bit different. We still have the struct danger, that's there, but we don't have the function pointer anymore. Now if we go to here, we have this buffer overflow that's happening on the stack. But now we don't have any sort of check. This time you have to corrupt everything yourself. There's no magic function pointer, there's no variable to be checked. You have to corrupt the stack frame yourself. When this return is called, it does some magic under the hood to go back to main here on this nested call. So how many bytes are we actually dealing with? This is one of the trickier things to figure out. My strategy for this is just going to GDB. So GDB is kind of a more advanced tool, I will admit, but I still think it's really worth knowing, especially for things like this. So we can set a breakpoint on nested, and this breakpoint tells the program to stop once we hit a particular point in the program. So like we're hoping for, it stops at the beginning of it. And we can go next, and now we're going to take in some data. So I'm going to write some characters in here, and this should help us figure out where we're going. Now we're at this return point, and this is where we have to start reading some assembly. So NOP stands for no operation, and that can be safely ignored. If you do SI, we go one instruction ahead, and this is just going to be restoring the value of EBX, I believe. After that, leave will fix all the stack frame information. After that, we get prepared to call ret. And at this point, if we look at the place at which the stack address is at, the stack pointer is at, if we do info registers, the ESP is pointed there, and if we do WX, we can see the value of there. So this is the point which we're going to return at, and this is the return address that we're going to go from. Now we can actually go look and see where our program or where our information was at. We can do something like 30wx, and the stack actually grows the other direction. So we're going to do something like 0c. And if you see here, we can actually see our data, which means we can figure out how many bytes we need to write in order to get to the magic value. So the ESP is currently pointed at this value, the 3C. And if we go back up, we started writing at D60C. So if we exit this and just do some math, we can do 0C minus this, and we'll figure out how many bytes that is. Do that in hex, that's hex 30 bytes, which was the hint that was given. So now we know exactly how many bytes we need to write in order to corrupt the return address. An alternative way to do this is to just overflow the buffer with characters that make sense, where you could do AA, A, B, 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 C, 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 and you do this until you've actually hit that overflow, and now you know where you're actually overflowing at. This is just the more scientific way to do it. So now we know how to overwrite the stack address. The next part to this, though, is not just the stack address. We need to know what we actually overwrite it with. So if we go back to our program, just like we did before, we also have a print flag function. That's fun. So with this print flag function, we can use exactly the same thing as we did before. The address is right here. I showed this how to do this in the previous challenge, but it's pretty easy, so I'll just show it again. We just go gdb corrupt ret, and if we do print flag, print is the command, flag is the global object we're looking at. It also prints this out. So I'm now going to go back here. I'm going to copy this because that's what we want. So as we learned, this is going to be hex 30 or 48 bytes until that point we need to overwrite. And then we need to write this in the little endian address form. So we're going to do hex 56, hex 88, hex 04, hex 08. And if we look at this in XXD again, we'll see that we indeed hit this correctly. With exactly the amount of bytes we need. So if we do this with our program, we've printed the flag again. So what we did is we corrupted the stack pointer, the return address on the stack, to jump to our malicious function. Now, this is exactly what we did before, except of writing the function pointer, we corrupted the stack address. And this is the classic buffer overflow method. Now, we bring it up another notch in difficulty in this next step, but I think it's really exciting. So, thanks for watching. Let me know if you have any questions. Bye.